Okay, so I'm not going to go back to remember what I was saying.
You need to have one button.
I have to, yes. Got it. But we didn't, just for the record, we didn't really get very far. Everything is here is in the lecture note that is available somewhere. Yeah. Okay, so one typical example. So how do you see that a proton consists of partons? The experiment that led Björkén to somehow start thinking about partons was deep inelastic scattering. In the deep inelastic scattering experiments in the 60s, I believe. So what happens in deep inelastic scattering? So deep inelastic scattering is electron scattering of a proton. So you have an electron coming in, an electron going out. You measure the electron. That's crucial. You always measure the electron. That's why DI is nice. And the electron interacts with your non-perturbative proton or nucleus by a virtual photon. So there's a virtual photon in this interaction. In this case, the transfer scale, you can, in this case, the kinematics, measuring the kinematics of this process, you actually only need to measure the outgoing electron, and you can reconstruct what was the X and what was the Q in this process by just measuring the electron. If you know the incoming electron, you measure the outgoing electron, you take the Lorentz 4 vector difference of these two and square it. This is what is called Q squared in deep inelastic scattering. And so here you see this is a perfectly Lorentz invariant quantity, but I think it's useful to think this Q squared as a transverse momentum. It's useful to think of it, at least in the small x physics. It's useful to think of it as the transverse moment, it's useful to think of this virtual photon having only a transverse momentum of this size and no longitudinal momentum and zero frequency. Or actually a longitudinal momentum and a frequency, but in such a way that the virtuality is just given by this transverse moment. And then in this case, you can also reconstruct X. So this is to be, if you want to be really strict, this is X Björkén. And this is X Feynman, and at leading order in QCD perturbation to the X Björkén, which is just the kinematical variable that you construct from the DIS experiment, is the same as X Feynman, which is the fraction of the proton's momentum carried by the parton. But for the purposes of these lectures, I'm not gonna somehow go into that direction. So this is X Björkén. In DIS, you can measure it. The interpretation is that of X Feynman, which is the fraction of the momentum carried. And so what the observation that surprised people at the time in the 60s about these DIS scattering experiments was that when you were able to relatively high Q squared larger than the mass of the proton, significantly larger than the mass of the proton, you started seeing that this cross section as a function of these variables starts looking like you are scattering off point-like particles when you're scattering off the proton. And until that point, it had not been realized that the proton would, I mean, there was no, at least evidence that the proton would consist of point-like particles. But when you look close enough, and this in the 60s, they first managed to look close enough, they saw that the proton actually consists of point-like particles. And the fact that they're point-like, this is just like the Rutherford experiment, seeing that an atom has a nucleus and a cloud of electrons. It is just repeating the same thing inside the proton. When you go to high enough scattering, from the scattering angles of the electrons, you can deduce that the thing is made of point-like things that are point-like. And these point-like things were called partons. Actually, of course, to be Feynman and Björkén, but I mean, everybody loves Feynman, and Björkén is not given all the credit that he deserves. So this is why I somehow bring out the name of Björkén. So okay, so this was realized in the 60s, and then after a little bit while, people realized that okay, the partons are quarks and gluons. And so what we're going to do in these lectures is study the small x partons which are predominantly gluons. So I'm not going to be caring about, for me, quarks are a higher order correction and gluons are the real thing. And you only need quarks when you go to higher order perturbation theory. So this will be mostly about gluons. The other thing about this, so the thing about these two variables, so the x and pt or q squared. Now, when you read about this kind of physics in a textbook, typical QCD, Haltz and Martin, I think, typical textbook that gives you an introduction to perturbing QCD or deep inelastic scattering, you will encounter the concept of parton distribution, quark and gluon distribution, right? Now, actually, so this concept of quark and gluon distributions come in what I like to use the term collinear factorization. And collinear factorization is a little bit weird. The way things are represented in textbooks is that these partons have only longitudinal momentum. When you take an elementary calculation of BIS in collinear factorization, the way the calculation is done is that you assume that these quarks and gluons only have longitudinal momentum along the momentum of the proton, no transverse. Then there's something in the process like the virtual photon that kicks them, and then you calculate this process assuming that they only have longitudinal momentum. And this you repeat at higher order. People calculate one loop, two loop calculations in collinear factorization, and you always do things as calculate. You always calculate in the way that the partons have only longitudinal momentum. But that's not actually the way you think about the process. So if you think of how this kind of a DIS event, for example, is implemented in Pythia, an event generator that has kind of a microscopical model for what these hard collisions are, or if you look at the actual derivation of this DGLAB equation, for example, the derivation of collinear factorization, these partons are not actually collinear. These partons have a transverse momentum. For example, in DIS, the partons that you are hitting actually have a transverse momentum of the order of q squared. And somehow the magic of collinear factorization is that if you are interested in high q squared, you are thinking, the way you think is that these partons have transverse momentum of the order of this q squared of the process that you are measuring, but you actually calculate as if they were collinear. And then the transverse momentum is taken into account by the fact that your parton distribution depends on this variable, this scale. So this is collinear factorization. This is kind of because you are looking at leading logs of q squared, and these leading logs are resummed into DGLAB evolution of collinear parton distributions. So you your calculational framework is that you have collinear parton distributions that depend on the scale. But what these actually represent is a collection of partons that have different KTs. Now, in this lecture, we're not going to go into collinear factorization, collinear perturbation theory. So in this when we start talking about these gluon, the distributions of gluons, these kind of partons, they are actually going to have a transverse momentum that is going to be explicit in our calculation. We're not going to be doing DGLABs because we are not going to be looking at high enough q squares that log q squared needs to be resummed. But if we are interested in saturation physics, I think it's better to keep it explicit, the fact that the gluons actually have a transverse momentum. And when you have a q squared, you explicitly have the gluons having transverse momenta. But then that means that kind of the relation to this collinear factorization is a little bit a further step that we will not do here. That gets more complicated. So that's kind of the direction in which we're going. As I said, this DIS physical process, Matt is going to cover that more. I'm somehow going into a little bit different direction. But this is our starting point. Our starting point is that the nucleus or proton is made of partons. Out of these partons, the gluons are the ones that are really interest us the most. And we are going to try to understand the properties of these gluons in a high energy high energy nucleus or proton. Good. So now I can leave that on, but now I'll actually start using the blackboard. And before we go to actual color fields, before we go to actual scattering, I'm going to send some lights somewhere. If I do this, is it gonna
If you're not in front of the board, there is no glare as soon as you step in front of the board.
What about this?
Let's see what happens. Okay, looks good.
Okay, so before we go to physics, I'm gonna talk a little bit about kinematics. Okay, as I said, in these lectures, the z-axis is special. So we're gonna break all manner of gauge and Lorentz symmetry because we're interested in the physical situation, which is very asymmetric. So we're gonna introduce two, to be able to talk about this kinematics. To talk about this, we're gonna do a little bit of kinematics and introduce two concepts that might or might not be familiar to you. And I'm just saying so that maybe I'll ask. So the first one is ask when I write these down, the definitions first. So the first kinematical kinematical concept is that of rapidity. So who has never heard of rapidity? Who has heard of rapidity? Everybody knows what rapidity is. Good. So I can be quick. So you realize that when I'm introducing rapidity in the z direction. This is where I'm breaking Lorentz symmetry. I'm choosing a coordinate system and a variable that treats the z direction very, very differently. So for a particle, let me get this right. Yeah. For a particle, the energy of the particle in some rest frame, in some whatever in the frame that we are looking at. So in this case, this is going to be the frame where the LHC detector sits. Okay, our collider frame. We can write the energy. We can go from transverse and longitudinal momenta to a coordinate system where energy is the square root of pt squared plus m squared. So pt is transverse. So pt is px and py. And then in the same coordinate system, p3 is the same square root squared times a sinh y. Now a quick calculation will tell you that if you calculate p squared minus p3 squared of pz of p3 minus pt squared, you will get m squared. For that, the essential thing is that hyperbolic cosine squared minus hyperbolic sine squared is 1. This
is E in your convention P0.
Yes, so this is P0 of energy.
Can we say anything about the transfer?
So the transverse momentum transverse momentum is just x and y. Okay, so this is there's no we are using the perfectly conventional transverse components, x and y components of a vector. It is just convenient to use a slightly different parameterization of the longitudinal, so P0 and P3. But these are for the transverse, we just have x component and y component, and there's no. And again, my physical situation is very Lorentz non-invariant. My physical situation breaks rotational invariance. And this is why I'm choosing a coordinate system that is also treats transverse in the normal way, but treats longitudinal in a very different way.
So this frame that we're in now is sort of the frame which this longitudinal dimension points in the z direction.
Yes. Well, in principle, I mean, I can define this in any frame. right? Any frame. This is just any frame where I have 4 components. I can write these 4 components in terms of this. But yes, this is practical. We are going to be thinking this is useful for the frame where the particle is going in the z direction with a high momentum, high energy. Good. So this is rapidity. There's also experimentalists talk about pseudo rapidity, which is almost the same but not exactly the same. Okay, and but let's not go there here right now. There's also at maybe towards the end of the week we will discuss space-time rapidity, which is this is called momentum space rapidity. So rapidity y, this is the rapidity. Space-time rapidity, which is the analog of the momentum rapidity for coordinates. So time and XYZ coordinates, you can do a similar transformation and go to space-time rapidity and proper time. Okay. Good. So that's rapidity. Then the other thing that we need are light cone, LC. So for that rapidity, light cone variables for any Lorentz 4 vector v mu, okay, I will define v plus and minus as 1 over square root 2 v0 plus or minus v3, right? So again, I'm 0 and 3. I'm treating a special way. My components v1 and v2, the x and y components are just normal. Okay. So these are light cone coordinates, so the light cone components of a 4 vector v mu. Again, you see that this is just a simple linear. The original v0 and v3 are just simple linear combinations of v plus and v minus. Okay. So good. So why do we do this? Of course, you can kind of see that. Think about a particle. Think about that if this v is the momentum of a particle, right? If it's a high energy particle, its momentum it's going very fast in the z direction. Its energy and the momentum in the z component of the momentum are going to be approximately the same. Right? If it's high enough energy, the mass doesn't matter. So in this case, v plus for that particle, or the p plus momentum plus component is going to be large, and the momentum minus component is going to be very small. So these are convenient for analyzing things that are particles that are going at high velocity, high momentum. So a simple exercise is to calculate the scalar product. So scalar product x dot y, two vectors x and y. So x mu, y mu. Well, I'm trying to keep my indices down separate. Everybody knows what the difference between, but it matters to have an index up or an index down. Yeah, so if I just calculate the scalar product, you can easily do it. You will see that it is x plus y minus plus y plus x minus x perp dot y perp. Okay, so these are now two-dimensional vectors, and this is a two-dimensional dot product. This is the usual minus of the. This is the usual minus of a plus minus 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 metric. Okay, Lorentz for vectors, and this is kind of you see x plus y minus y plus y, y plus x minus. After a little bit of plugging this back in, you'll see that it actually gives you the right thing. V0 squared minus V3 squared. Okay. So that's a scalar product. And thus you know that this is index up and index down. This means that the metric is not diagonal. So in these components, a V plus is the same as V plus up is the same as a V minus down. And V minus up is the same as a V plus down. Okay. Unfortunately for you, and unfortunately for many, math is possibly going to use a different convention here, because math is a disciple of Yuri Kopchikov, who's a disciple of Al Muller, and somehow they put pluses and minuses up and down in a way that I don't even fully understand. Yeah, it's not that I haven't even seriously tried to understand, because I'm wedded to this convention, and there's this different. Also math, if he has these plus and minus components, his square root of 2 might not be there. He might not have the square root 2 here. Or some people have put a plus, just a 1 here, but then if you lower the indices, we have a 2. Whereas in my convention, it's always 1 over square root 2. These different conventions are known as, mine is the Kogut-Soper convention. And what I think Matt might use if he goes into this coordinate system is the Brodsky-Lepage convention. So unfortunate confusion here. So just be aware of, if getting factors of 2 and square roots 2 right or wrong in following 2 different sources happens very easily. So just a word of caution, okay, about these conventions. Good. A little bit more. So a high energy particle will have a P plus, which is very large. Okay. So high energy particle will go in the positive Z direction. It's going to have so PT is PT, but then it will have a P minus, which is PT squared plus M squared over 2P plus. Again, it's easy to notice that if you notice that P squared, which is M squared, is 2P plus P minus P per squared. A special case of the scalar product for the square of the vector P squared is 2P plus P minus P squared. From this, you can solve that P minus is P plus. So this is a high energy particle, has a very small P minus. Okay. It has a large P plus. So the order of magnitude, I think maybe Thomas, if you get towards the very end, you will kind of be having in some sense similar, maybe a covariant formulation of a similar thinking in terms of orders of magnitude. There's a large component, which is the plus. Then there's a transverse, which is a little bit smaller, and then there's a minus, which is even smaller.
And there will be, of course, exactly the opposite convention, no square root of 2, minus very much plus.
So full of confusion, and maybe presumably you will write this in a kind of maybe a covariant way.
I just introduce a reference vector, but this is the same as you do. You introduce the reference.
Yes, I introduce a reference vector, which is I introduce a reference vector which is in plus Z direction. You introduce a reference vector that can point in A direction.
What is the denominator there for the P minus?
P plus, 2P plus.
2P plus.
This is for you somehow the P per squared and the M squared seems to be of the same order of magnitude that you keep.
Yes. Yeah. So this, I forgot to say that this is sometimes, although not often these days, this square root is referred to as imperp. So PT squared plus M squared is sometimes known as imperp, or the transverse mass.
You wait 10 years, you will have about 10 new abbreviations per year added up.
I think the transverse mass is something that I think maybe experimentalists. Well, anyway, this appears in some. This is a kind of natural. This combination naturally appears. So typically, mostly my particles are massless. Okay, but somehow, for me, the PT and the mass are going to be they often appear in this combination, and the PT and the mass often appear in this combination, and for many of the physics that I think of, it doesn't matter if this transverse mass comes from the mass or if it comes from the PT. It's a transverse mass. Okay, but depends a bit on the situation. It's somehow they naturally go together like this. Good. So that's a high energy. That's what a high energy particle looks like. And then a final thing, if you actually want to do calculations, and somehow my talk is mostly going to be mostly going to be kind of waving hands and discussing the physics, but sometimes you actually want to do a calculation. There's note that a Lorentz invariant phase space measure. Okay, when you do integrals in particle physics, you often want to integrate over a momentum. You do this in a Lorentz invariant way. So Lorentz invariant phase space. So the Lorentz invariant phase space is integrating over 4 components of the momentum divided by 2 pi to the 4. Okay, and to make it a Lorentz invariant phase space for particles on mass shell, you put in a delta function of p plus minus m squared. Has somebody never seen this kind of are you used to doing this kind of things? Some particle, I think some elementary, even if you don't go to quantum field theory, you just have elementary course in particle physics where they'll tell you what a cross section is. You probably, but if you haven't, ask now or ask in the evening. So D4P, one of the really nice things about this 1/over square root convention is that now my D4P is DP plus DP minus without the factorial. Without a Jacobian. Okay, so let's work this out. This is because I have a 1/over square root 2 here, and this is dp plus dp minus d squared t over 2 pi. Oh, and of course I have a 2 pi here. Sorry about that. It's always when there's a delta function, there's a 2 pi with the delta. Sorry about that. So actually it's a 2 pi to the 2 pi cubed here because I cancel this out. I write this out and it's a 2p plus p minus p per squared like this. And now I'm not gonna really go into discussing quantization and finer aspects, but now and then kind of there are these terms that appear kind of pop up in my words, which is the term of light form quantization versus instant form quantization. So what you do when you learn quantum mechanics, and even when you learn quantum field theory, you learn what is called instant form quantization, where the time is time, right? Okay, so and this is an aspect that is usually not when you learn quantum field theory or quantum mechanics. It is not necessarily often explicitly said, although it's always there, is that you start when you do quantum mechanics, you do have commutation relations, commutators between operators. This is the kind of when you get into quantum mechanics, this is what you do. And then at some point you go to the Heisenberg picture where these operators are time dependent. And so what happens is that, which they don't necessarily always emphasize is that the commutation relation for these Heisenberg operators, what you know are equal time commutation relations. So you know what the commutator of operator momentum and coordinate operators, when they're Heisenberg operators, they're time dependent, and the canonical commutation relations are at equal time. So you need to know what a time coordinate is, even if you're unless you do path integrals, then it's manifestly covariant. but when you do canonical quantization or kind of quantum mechanics in the Heisenberg picture, there's a time. Time plays a special role, and it plays a special role in the quantization process, right? So, without going into details, I will kind of implicitly in back of my head, I will be doing light cone quantization, where the coordinate, the plus component of the coordinate, x, y, z here, the space-time coordinate, is a time. It's a light cone time. And then the minus component of a space-time coordinate is a spatial component, spatial time coordinate. And because of my funny, this funny metric, x naught y, if x plus is the time, if I calculate, no, maybe I should just write it. Maybe I should write it. If I calculate e dot x, this is going to be e plus x minus plus e minus x plus minus e dot xt. Now, if my x plus is a time, my p minus is an energy. So on the light cone, I live on the light cone, I'm so fast. The p plus component of a momentum is a momentum. I think of it as a spatial momentum. For me, p plus is a spatial momentum, and p minus is a light cone energy. So for me, p plus is momentum, and p minus is energy. And therefore, for example, when I'm doing light cone quantization, my p minus is my light cone Hamiltonian, and a p plus is a coordinate, spatial coordinate. So that's why, if you have encountered this in your elementary particle physics, what you do next is that you integrate over P0, right? Integrate over P0, then you get momentum from massless particle. So you integrate over the energy. So what I want to do is I want to integrate over the energy. I'm going to integrate over dp minus and write my Lorentz invariant phase space as d squared over 2 pi squared. And then if I'm integrating this delta function, I'm integrating over p minus, and I need to pull this kind of, to get this into a delta function of p minus minus something, I need to pull out this factor. I pull it out in front, it becomes because the delta function is like a dimensionally delta function of x is dimension like 1 over x. So this one goes downstairs, and what I get is dp plus over 4 pi t plus. Okay, so a Lorentz invariant phase space element looks like a dp plus over p plus. And if I now use where is this? On the board. It is an easy exercise that I will leave you to do at your leisure to show that for a momentum, which I'm using this rapidity, p plus and minus is 1 over square root 2 p per squared plus m squared exponential or plus or minus y. Okay. So this is the rapidity. This is the plus and minus components and the rapidity. So here's the relation. Plus and minus components are just exponentials of rapidity. I mean, and with the convention for this. So here, if I look at this, you see that somehow by differential, so the convention is that plus, and so this plus corresponds to this plus, this minus corresponds to this minus. So from looking at this a little bit, I see that actually my Lorentz invariant phase space element 2 pi squared is actually 1 over 2 pi dy. So I have a dp plus over dp plus, which is actually a dy. So somehow the Lorentz invariant way to integrate over phase space is to integrate over transverse momentum and integrate over rapidity. And if you have encountered this rapidity, you know that in a Lorentz boost, if you do a Lorentz boost, rapidity is the convenient variable for a Lorentz boost, because if you boost by some velocity, the way to actually do that boost is that from this velocity you calculate, you associate this velocity with the rapidity, and then you're boosting with the rapidity, and when you boost with the rapidity is just additive. So this rapidity is shifted, gets an additional term, y goes to y plus the boost. So you see that because the rapidity is additive, these plus and minus moments boost in a simple way. So when you're Lorentz boosting along the z direction, those boosts are, I'm breaking symmetry and I'm making it easy to boost in the z direction. I'm making it difficult to go in other direction, but I'm making it easy to boost in the z direction. And in the z direction, p plus and p minus are just, p plus is multiplied by number and p minus is divided by the same number in such a way that p plus times p minus stays the same. So somehow this is if you don't, you always get this when you integrate over dp plus over p plus. It's a rapidity. And somehow rapidity is that you learn in this business, you learn to think about things in terms of, you learn to think about the phase space in terms of transverse momentum and rapidity. There's the natural way to how many gluons, how many photons are there in an electron. So to a first approximation leading order at small x, the density of photons per unit rapidity is a constant. And so because that's the boosting. At high energy, things are boosted invariant, and having a distribution that is constant per unit rapidity is the natural thing to have. And so the intuition is that when you count gluons in a high energy proton, you count gluons per unit rapidity. And for first approximation, it's a constant, and then you look for deviation from that. Okay, so rapidity and life cone variables, those are two technical things. And now we are an hour past, so I suggest we take a break, 5 or 10 minutes, and then we start discussing iconal scattering of a classical gauge field, the iconal approximation. So let's say 10 minutes.
10 minutes
10 minutes.
sounds good to me. Right, I'll stop recording and
Okay, so we're discussing high energy scattering, and of course, which means that we're going to be making approximations that the energy is high, and we want to be, because the reason you always study some limit in physics is that you want to use that limit to make simplifying assumptions. Simplifying approximations, right? You want to find a small parameter, expanding power series of that small parameter. So here we are working in the high energy limit, where we want to make our life simple by using the assumption that the collision energy of our collider experiment is much, much, much higher than any other scale with dimensions of energy, right? And so we want to use this to simplify our life. And in terms of scattering problems, the iconal approximation is an approximation that somehow puts into action the way to this somehow the fact that we have a high energy. So iconal approximation is a high energy approximation that allows you to make scattering look simpler. So one can think of iconal approximation in different ways, but we will start with an iconal approximation in scattering of a classical field, classical classical potential. So quantum mechanical particle scattering of a classical field. So why classical field? Of course, classical is simpler than quantum, but this is also related to the fact that in gluon, so when we study gluon saturation, we will be approximating our proton or nucleus, the small x degrees of freedom of the gluons of this proton or nucleus, by a classical field. The idea is going to be, and so both me and Matt, maybe Matt even more, are going to talk about gluon saturation. Somehow the idea is that saturation means that there are many gluons, some limited phase space, and somehow when there are many, when the occupation number of a quantum state is high, this means that you are in a quantum mechanics or quantum field theory goes into a limit where a classical field approximation is valid. So quantum field theory has wonderful property that it contains classical fields and classical particles as appropriate limits. And we're going to go towards a regime where we use the classical field limit of QCD to understand energies. So this is why we'll start with iconal scattering in a classical field. So let's first start with to simplify our life, with a classical abelian gauge field. A mu, which depends on x. Okay, so there are different versions of the iconal. If you look at the Baroni and Bertazzi book, for example, they do iconal approximations, non-relativistic quantum mechanics. Then you can do iconal, and we'll look at iconal approximation in as iconal vertex in a frame. What is an iconal vertex in a Feynman diagram calculation? So this is kind of one. There are several simplifying things that one can either do or not do. But I somehow like this particular set of simplifications, but not too many. So we have now, and now I'm doing again. I promised I'm not going to do quantum field theory. I'm just going to do, in this case, I'm just going to do elementary quantum mechanics. So I'm going to be looking at the quantum mechanical particle, scalar particle, which is propagating in a classical external abelian field. So scalar particle, but I do want to be relativistic because I want to be high energy. So what I will do is that I will consider the Klein-Gordon equation for a scalar particle in this kind of a classical background field. So let me write the Klein-Gordon equation. Mu, I'm always not very consistent with my signs. Plus a mu up, of course, phi is 0. So now I have a scalar particle, which is a wave function. It's just a relativistic wave equation for this phi in a classical background field, a mu, okay, which is 0. Oh, and my field is massless too. Just, I don't think the mass would really. Oh, I can have a mass. Sorry. I did have a mass in my notes, but it doesn't really matter that much. Okay. So this is the equation, and now we're going to be interested in a scattering, high energy scattering problem. So we are going to be interested in kind of solutions where we have a particle coming in from -infinity in the z direction. So I'm going to be interested in a situation where at x plus going to -infinity. So this is far past for a light-like particle going in the positive direction. My solution should go like, should approach just a plane wave. I'm looking for something that represents the physical situation of just a plane wave, free particle coming from -infinity. And and so the solution, I'm looking for a scattering solution with this equation, with this kind of a property. Okay. So what we'll do is then in order to be able to use the iconal approximation, I will use the following ansatz for the solution of this full equation. I will say that the solution of the full equation is phi. This is my solution of the equation. This asymptotic minus I k dot x times another phi. Okay. So this is just an ansatz. I can always make an ansatz, but here comes the approximation. Now I decided I want to look at the high energy problem. So I want to look at a situation where my incoming particle, which came in from minus infinity, it has a momentum form momentum k. I want to look at a situation where this k plus is larger than anything else. Okay. So in particular, this k plus is larger than any other momentum, any other derivative of any other thing. So let me kind of generically write this as that any derivative. So derivative of a function divided by the function itself kind of gives you the rate of how fast the function changes. And I'm going to assume that k plus is larger than any quantities like this. Okay. And then I'll also use Lorentz gauge. I will assume that my background field satisfies the Lorentz gauge condition. Okay, just to make my life simpler. To some extent, maybe I could do without this, but not as we'll see, I'm not able to do this in full generality. The iconal approximation has some implications about gauge choice. Okay, but this was an ansatz. So I just plug this ansatz into my equation, okay, and see what we get. So at this point, at this level, you see that this approximation means that this derivative does not act. I mean, this derivative acting on this gauge potential gives me 0. So I can kind of, with this assumption about the gauge, I can all of these derivatives only act on the phi, but the phi is a product of the plane wave and another phi. So I need to take these both of these into account. I'll move the m squared to the left-hand side. What I get is that I have two derivatives. Okay, so I'll split out the terms where both of these derivatives act on the plane wave. Okay, so I have a id mu acting on my exponential minus ik, that gives the I minus and the I cancel, and what I get is just k squared. So this and this both acting on this gives me k squared. Then I take the minus m squared like this. Okay, so that was easy. Then I have two cross terms where I have plus 2 e a mu, and then so cross term between the gauge potential and the derivative, so this and this, or then the other one, this and this. Acting and the derivatives acting on the exponential here. Okay, and then there's another term, another two terms where I have two derivatives, these both derivatives, one derivative acting on the exponential, the other derivative acting on this function. Okay, so this is plus 2 k mu d mu, and now this derivative is going to be one that is acting on this, so I will actually write this exponential I k dot x. I have already taken care of minus I k dot x. I'm explicitly taking care of all the derivatives acting on this fluctuating factor, and only keeping the derivatives acting on this phi. Good. And then I have a bunch of other terms plus 2. I have to cheat from my notes. I e a mu d mu. So I have terms for cost terms with this derivative acting on this and taking an a, and then I have a term with plus e squared a mu like this, and all of this acting on my function phi. Okay, and this, I hope this is everything. Okay, so then let's look at this, simplify this. First of all, my incoming particle is on shell. So this and this cancel. Okay. Then I'm going to use the fact that my K plus is larger than anything else. So I'm really interested in just the high energy limit. So what I use this high energy limit for is that out of this whole thing, I only pick the terms from this Klein-Gordon equation, which have a positive power of this large parameter. Okay. So this means that here there's no K. So I can neglect these. These are much larger than the K plus terms. And also here, the only term that I pick from here is the one where there's a K plus component. So in the limit, K plus going to infinity, my Klein-Gordon equation, I can just cancel the two. I can cancel the 2e. I can take the K plus. I take the K plus as a common factor, and what I get is d plus, remember, index of so K plus d plus, and d plus means d over dx plus. I will have to be really careful with index up and index down now that my metric is non-diagonal. So d plus is derivative with respect to x plus, where x plus is index up. Okay. So here I get a d plus, and from here I get a plus. I cancel the 2. So we should, oh yeah, e a plus 5 equals 0. And now I'm doing a mistake because I should have here I inherited this there was an I, because this was I get the K I, and derivative gives me a K, but the other one is still an I times derivative. So here I have an I. Okay. Let me write this in another way. D plus minus a minus 5 is 0. Okay. So, and the claim is that this simple equation tells me the most important part of my scattering problem in the limit of high energy. Okay, so what is this? This is a simple equation that I can solve. This means that my phi of x is going to be exponential of I, E, and D. So derivative in the plus direction. So I'm integrating in the plus direction up to x plus, that's the upper limit, and from some lower limit. I think the lower limit should be minus infinity, because I want this phi to become 1 in the limit of x plus to minus infinity, and then a minus y. Right. So this is the solution, right? This thing here, so it's a solution. It's not a perturbative solution in the sense that it's not a power series. I mean, it reads some series of powers of the coupling constant and the gauge field, right? But it is an approximative solution because I have used the icon of, I have used the high energy limit, and I think this is kind of the thing that repeats itself all the time in the saturation physics. One is doing a coupling calculation. This here the coupling isn't really visible, but one is doing a non-perturbative calculation. But it's not an exact non-perturbative calculation. It's a non-perturbative calculation where I use the fact that we assume the energy to be very high. Okay. And this this thing. Oops. Yeah. Then good. So if I want to, so this is now I have my solution, right? This is. Let's take one more step and ask, what does this Klein-Gordon equation tell me about the scattering problem? I want to study the case of a. I want to study the case of a particle coming in from -infinity, going through the field, and then scattering. And I'm interested in, okay, where did this particle scattering? Came from there, interacted, and then it goes there. It's the cross section. Okay. I'm not going to be very precise in trying to tell you what somehow derive what the cross section is. I will just tell you what the cross section is. Tell you what the cross section is. So to get the cross section, of course, we want the particle coming in from -infinity. You want to go to +infinity. So we want our phi at x plus going to +infinity. So this is going to be exponential of I minus k of x. And then let me write this in this kind of a funny way that I will separate out one. This was the incoming wave. But of course, my solution was just like the incoming wave times this exponential. So I don't actually have such an exponential, so I have to subtract it again. I subtract 1 minus 1, and then I write this as I have a minus. I have to have a minus here, like this. And then I'm going to +infinity. So here I have an integral from -infinity to infinity, dy minus y plus a minus x. Like this. Okay.
That x be a y. A of y.
Oh, absolutely. Good. Good. So here's my outgoing wave. I just introduced the 1 minus 1 by hand. So here, this thing here is something that is sometimes called the iconal phase. Just somehow name for it.
Sorry, could you just explain again why you did that 1 minus 1?
I'm coming to it. Just there. So this is the iconal. This is known as can be called the iconal phase. Okay. So you kind of see that in this approximation, it's funny. There's an interaction with the background field. The only thing the classical field is it changes the phase of the wave. But all the physics is in that change of the phase actually is scattering. Right? It kind of doesn't sound a bit weird maybe in the beginning, but that is scattering. So now let's come to why did I separate out the 1 here? Usually when you want to get in a scattering problem in quantum mechanics, somehow think of scattering in quantum mechanics, not necessarily scattering in field theory. What you write is that if you write the solution of the Schrödinger equation in 2 terms, as a sum of 2 terms, you separate out the incoming wave. I put this because I want to separate out the thing that was coming in, my incoming particle. And then kind of a standard exercise in quantum mechanics textbooks is to see that, the rest is the scattering amplitude up to some normalizations and so on. So I have one kind of in the note, there's a quick and dirty calculation of how this normalization goes. But here I will just, for the purposes of simplicity, I will just state that, okay, this, in fact, here is basically now the scattering amplitude. Apart from a little bit of 2 pi's and so on, but what I will just state, and there are ways to do this carefully, but I'm not going to take the time to do that. I will just state that now my calculation as I've gotten this far, I've solved the Schrodinger equation or the Klein-Gordon equation really. And what this has given me is this 4, and from this I just read off that the elastic cross section, this is elastic because I have this one particle coming in and the same particle is going out. It's not disappearing anymore, there's no absorption. Yes. So this is elastic. Elastic cross section is, and I will take an absolute value. There's a 2 pi. Now to get this 2 pi, I mean essentially this 2 pi has to, it kind of goes together with the q squared. Always when you have d squared momentum, there's it's 2 pi d squared momentum. I'm just writing the 2 pi on the right hand side of the equation instead of the left hand side. That somehow it is not really important for the physics. D squared x per exponential of minus I q per dot x per. So you see what I'm doing. This is in coordinate space. I'm Fourier transforming. Okay, I'm Fourier transforming to coordinate space, and then 1 minus exponential of I e minus infinity to infinity e y plus a minus y parenthesis absolute value squared. Okay, so now I have calculated a cross section from this, and there's in the notes there's an attempt to justify a little bit the pi's we have to choose. Okay, but those are not important for understanding the physics. So you see, kind of one of so there's several things. We integrated over y plus or x plus. We're Fourier transforming explicitly the transverse coordinate. So kind of this is an integral over along the path of the particle, light-like path of the particle in the classical field. I'm just integrating, and I'm multiplying by I and exponentiating. So I get a phase. This phase is a function of the transverse coordinate, and I'm transforming from the transverse coordinate to momentum. And this gives me the cross-section differentially in the momentum kick that I get from the classical field. What I'm pushing under the carpet is that I'm not saying anything about the x minus the coordinate here. And to some extent, we will come back to this, come to the x minus later. But here I'm just hiding under the carpet that I haven't really told you anything about x minus. If you compare the Baroni and Predazzi, for example, they do this calculation of a classical optics calculation, light going through a hole, and then light going through a hole, then you expand in a radial spherical wave. Or if you look at elementary quantum mechanics scattering problem, but the outgoing wave doesn't exactly look like this. The outgoing wave looks like a spherical wave. Okay, so this is not written in that way. I think you can probably do it if you want, but it doesn't really matter because we are in the Eikonov approximation. We are looking at small angle scattering. So the fact that this doesn't exactly look like a spherical wave, we don't really care about it because we're just looking at a small scattering angle. Okay, so we're not being that careful about this. So what is in here is so this other things, this minus I, of course, this is inside the absolute value, so it's kind of completely and doesn't quantitatively mean anything. I just put a minus I here, which inside the absolute value I could have taken this to be 1. That is just because there's a convention of the phase of the scattering amplitude. So there's a convention of how you normalize things and what you call the real part of the scattering amplitude and the imaginary part of the scattering amplitude really have well-defined conventional meanings. So if I want this to be kind of if I want the thing inside the square to be a scattering amplitude in the usual way, I need to put the minus I there. That's one thing. Another thing is that since now we're talking real imaginary parts, there's an exponential of I something. So if you start expanding this in weak coupling, and now you can of course recover weak coupling results by expanding in this. This is the QED coupling constant. The first term in the expansion goes away. That's one. The next term has an I which cancels this minus I. So the first term is real. So the leading order scattering amplitude is real. Then when you go to next order, there's an E squared part of the scattering amplitude, which is imaginary because you get two of these I's and there's a third I here. So there's so this represents and somehow, even though we made approximations, these approximations broke some things, but they didn't break all possible things. One of the things that was not broken was the fact that we have an amplitude that has real and imaginary parts. It's an amplitude that it satisfies the requirements of unitarity. Unitarity poses some constraints on scattering amplitudes because time evolution has to conserve probability in quantum mechanics. And that leads to constraints on scattering amplitudes, like the optical theorem, most important. So what does the optical theorem say? The optical theorem says that the total cross-section is given by the imaginary part of the forward elastic scattering amplitude. And times 2, when depends if there's a 2 or pi or whatever, convention dependent thing. But the essential thing is imaginary part of the forward elastic scattering amplitude. So here we have a forward elastic scatter. Here we have an elastic scattering amplitude. We can we can extract the forward elastic amplitude by forward means Q perp is 0. Forward means Q perp equals 0, and then we can this forward amplitude has a real and imaginary part. So kind of we can and somehow, and I think even though we made approximations, we did not break, for example, the fact that in the optical theorem, we didn't break the fact that the total cross-section is given by the real part of the forward elastic scattering amplitude. That still works. So there's kind of a somehow built-in unitarity require relations between different orders of this thing and different orders in this expansion that are still okay. So that's one of the important things about gluon saturation, because gluon saturation in the rest frame where we look at it, and I think Matt Siebert also, it's actually nothing dynamical. It's just a unitarity requirement. It's somehow something that is needed because scattering amplitudes have to obey unitarity, and that automatically results in gluon saturation. Gluon saturation is what keeps scattering amplitude unitary, and you kind of get it exactly from this kind of expressions where you have exponentials of gauge fields. Good. So that was so a lot of kind of things in this iconal scattering form. Just at this point.
So you said in the ansatz, of course, you can split off whatever factor you want, but then it was important that somehow the problem is such that this exponential basically captures everything up to a small residual momentum.
Yeah.
And that also this background field scales in the same way as this residual momentum.
Yes. So kind of again, it's the iconal approximation. There's one K plus is larger than anything else, larger than any gradient of the background field, or larger than any residual. Obviously,
you're not allowed to have modes in A, the photon in this case, that would compete with the K plus.
Compete with the K plus.
Or if there's some solution which is not a plane wave, but that's something different in the context.
Yes.
Of course, you will
Yeah.
I'm looking forward to getting explained why this. This is indeed all fulfilled.
Well,
Physics skills.
well, yeah, we'll see if I can satisfy you there, but yeah. So this was the QED, Klein-Gordon case, not even QED. Okay, so let's now go do a little bit further what we need to do. Two extensions, or one extension which is, well, two very important extensions. What if we hit a colored target instead of an abelian field? What changes? And also what happens if the scattering particle that is scattering is not a scalar particle, as in the Klein-Gordon equation, but some slightly more complicated, also different representation of the Lorentz group. So let's.
Sorry.
Yep.
I just want to ask, oh, I just realized where you're going. So, because we had the mass before, does the mass just get erased in that case?
Well, the mass cancelled because kind of the mass cancelled
Okay.
here. Yeah. And then of course, so what here we picked, or here we picked the coefficient of K plus, and of course, if you want to express this K plus in terms of Kz and K0, the mass is there, right? The mass, the mass. If you want to go from this K plus to other coordinate systems, the mass influences that. But otherwise, the mass didn't disappear. It is just that somehow we're looking at it in the system, in this coordinate system, and in this variables, the K plus is big. Leave this here. So okay, so now let's ask the next thing, which is what happens if we have color? What happens if we have color in our iconal scattering problem? And this, of course, is very important for QCD, okay? Because the gluon saturation, and that's what gluon saturation is. That's what probing gluon is. That it's a proton or nucleus that has a large enough, that has many gluons, that so many gluons that they can be viewed as a classical color field, and you're probing this in a high energy condition. So this is the CGC. So we have some probe particle. Here's our proton or nucleus. By the way, that one of the things in the jargon in the field that you might or might not have encountered. So capital A refers to nucleus. Capital A is the symbol that is used for the mass number, but by extension in the jargon of the field, when you talk about, let's say, PA scattering, it's proton nucleus scattering. So capital A is a nucleus. So here we have some colored particle that is going through the color field of a high energy nucleus, and we're going to describe this as a classical gluon field because it's a high energy. It's a high energy problem. It's a high energy collision, and we assume that there are many of these gluons, so this is classical. Okay, so let's consider somehow for a change. Why not consider a quark? I don't think it really matters if it's a quark or a scalar particle, but since we have quarks that have color, so we don't need to. Now we're actually doing the real physical theory. I'm not sure about my design here is whatever. So instead of the Klein-Gordon equation, we now have a Dirac equation. Okay, so IV slash minus A slash. So we can solve the Dirac equation the same way as in the Klein-Gordon. So I'm going to put an ansatz. We're going to put in an ansatz where psi is I use a particular letter here. Yes, of course, I need to use B. times minus I. Otherwise, for some reason I used P instead of K. And then since these are spinors, I also need to have a free spinor. So here's an ansatz for this equation. Psi, the solution of this equation is some V, which is unknown at the moment, times a plane wave, times a U of P, the Dirac spinor. So where you realize that if this V is 1 and there is no field, then this is a solution. This time I left out the mass. Yeah.
So it's maybe basically this I on a scalar.
Psi is now a spinor field with 4 components, and the 4 components are here. Okay. So 4 Dirac components. But then if this is an SU3 color field, it also has 3 color components. So psi has 3, which is MC, times 4, which is Dirac gamma matrix components. And this is the kind of the Dirac spin part. But this talks to the color part, that's because this B is going to have to do with the color field here. So I'm plugging this ansatz, and then I mean the manipulation is the same as if in spirit the same as we did for Klein Gordon. You recognize one thing that you recognize is that so when you pick out the large P plus, there's a P plus from the P, these Dirac slash, you always pick the gamma minus matrix because somehow it's a P plus gamma minus. So there's one specific gamma matrix is one gamma matrix is special. So it affects the spin components. I mean, in fact, it means that all the spin components of the quark interact in the same way. This approximation. But this is kind of a side remark. So you plug in this ansatz, you do the same thing, and what you end up with is the following. Equation that D plus this V is going to be, I'm not sure about the sign, but in my notes it says IG A minus B, right? So this is the same equation that somehow you see that in the abelian case. This is an easy differential equation. In the abelian case, the exponential was the solution of this equation. Right? In the abelian case, this was a number, this was a number, this was a number. It's a differential equation that is just the exponential exponential of the integral. Right? Now we have to be a little bit more careful because these are color. This is an NC times NC matrix. This is an NC times NC matrix. And this is an NC times NC matrix, so they don't commute. So I have to be a little bit more careful with what the exponentiation is. So, who has heard of a path ordered exponential? So you encounter path ordered exponentials typically in two places. In just advanced quantum mechanics scattering theory, where you have a time ordered exponential of the scattering operator. This is what the Dyson series, and this is how you define perturbation theory. And then once you have the Feynman rules, you forget about it completely, and you just use the Feynman rules. So the other place where you need path ordered exponentials is in QCD, when you want to do almost inevitably when you want to do QCD. So the solution of this is not an exponential, but a path ordered exponential, right? So the solution, let me just write the solution like this, but the solution of this is that this V this is my path ordering symbol, and exponential of minus I G derivative with respect to the plus coordinate. So this is up to x plus. I also want to integrate down from minus infinity because of course the boundary condition for my V is that it should be 1 in the past, right? But up to x plus d y plus a minus of y. And the definition of this path ordering symbol is that the path ordering of, say, a plus make this u plus and v plus is, now I have to think which way is my path ordering. It is the way I define this equation is that the way I think of it actually, well, let me write the definition first. It's if u plus is larger than a u plus goes to the right, and if v plus is larger, so it's always that plus a. So you can, it takes a, if you have never seen this, it takes a little bit of time to play around with this to understand somehow get familiar with this. So this is the way it's usually written, that somehow there's a theta function and we always kind of take the later time to the left. So if u plus is larger than u, that the corresponding a is to the left. And if v plus is larger than u plus, then the one at v plus is to the left. And somehow the way you connect this is that you just expand the exponential and take care of these orderings, and you see that it satisfies the differential equation. The way I actually think about, I never actually think about it in terms of this equation. When I see an expression like this, the way I think about it is that, okay, here I have a differential equation. I'm going to differentiate my v, and I'm going to differentiate my v with respect to the upper limit of the integral. And somehow this path ordered exponential has to be such that the upper limit of the integral is this a minus at x plus at the upper limit. And at the upper limit of the integral, this a minus has to drop down and come to the left. So if it drops down and comes to the left, then it's path ordered specific. Of course, somebody else uses a different convention, and you can use a different convention and have this a minus appearing on the right, and then it's the path ordered exponential in the other direction. You shouldn't somehow worry too much about it. When you understand the idea, you can always work out the conventions later. And there's no unique convention there. Okay, so this is the solution of. So this is the solution in the case of a colored particle. So this iconal phase gets replaced by this V, and of course in the scattering problem, you then take this V at x plus going to infinity, and then you get a V which only depends. Again, I'm sneakily forgetting the minus coordinate here, and I'm just saying that okay, you get a V and SU3 NC times NC that depends on the transverse coordinate, and this is known as the Wilson line. And everybody will happily tell you more than you ever wanted to know about Wilson lines. Just ask him, and he will tell you. He will tell you a lot. So this is the and the Wilson line actually somehow the physics of gluon saturation. The physics of gluon saturation is somehow the part of the idea is that when you want to study a regime that is dense gluonic regime, so many gluons, they are kind of strongly interacting non-linearly somehow. What it actually means is that somehow counting how many gluons there are is not the right way of understanding. The number of gluons is not the right degree of freedom. So in the CGC calculations, actually the quantity that you are working with is not the number of gluons. The quantity that you are working with is the Wilson line. So instead of parameterizing the gluon field of a proton by asking how many gluons are there, 5 or 7, right? That's not the way you ask the question. The way you quantify the gluon field is to ask what is the scattering amplitude of a high energy probe when it goes through the gluon field. The scattering amplitude is basically this Wilson line. And that's the quantitative degree. You don't ask how many gluons, you ask what's the Wilson line when you go through it. And you calculate things in terms of this Wilson line. And this is what we'll do tomorrow is an example of calculate a simple physical process in terms of this Wilson line. Now, I'll say two, a few more, two more things. I won't do any more calculations, but I will say one thing before we finish. But before I say that one thing, are there questions about?
Maybe I missed it, but what about this makes it color field specific to the fact that it's SU?
Yes, so the fact that this is an SU, it's a color. I've written the Dirac equation right here in the way that this is a vector in color space. And if this is a vector, then this is a matrix in color space. Right? And also this field is a matrix, an exponential of a matrix is a matrix. Okay. So this V is an SU NC matrix. It's a unitary matrix in the group because it's an exponential of minus I times. This is a permission matrix in the algebra. And the exponential is a unitary matrix in the group.
You two guys need to nod a lot.
Good. So before we finish, I will just write one formula on the board. So you might wonder, we did a scalar, and then we also did now. Well, we didn't really do, but I told you that the result is the same for a spinner. So of course, so there's two things here. We use the high energy approximation, and then we use the classical field. Now you might wonder, what if you don't want to use a classical field? You want to do a proper quantum field theory calculation, but you still want to use the kinematical approximation. So one way of doing that is to use the so-called iconal vertex. Iconal vertex, and an iconal vertex is the following: that you have some like this. I have a high energy particle, any particle, quark, gluon, lepton, electron, whatever. So could be scalar, could be fermion, could be gauge boson, could be a gluon itself. Okay, which comes in and then interacts with a gluon field. And I'm assuming that somehow P, let me put it this way to be that this has a high energy, high plus component. It scatters at small angles, so it comes out also with high energy. And so that this four momentum Q, is all the components are smaller than this P plus in every way. Okay. So now it turns out that if you want to use the high kinematical approximation in the Feynman diagram calculation, and this could be a quark, it could be a scalar, it could be a gluon itself. This particle could be anything. And the Feynman rule you use for such a vertex is just always I. Oh, and there's nu is the polarization vector of this gluon. Okay, and the Feynman rule for this vertex, the iconal vertex, is 2 IP mu, and then color factor. So the color factor depends on if this is a photon, the color factor is 1. If this is a gluon, and then this is a adjoint representation. But in some color representation, the color factor depends on the representation of this particle. Okay. But that's it. So the 3 gluon vertex, for example, if you go to this limit, it reduces to 2I p mu, and then there's a further simplification that the spin of this particle is the same as the spin of this particle. So an iconal interaction in the iconal limit interaction with the gauge field, it has a very simple form. So that's why we like the iconal approximation, because it simplifies. You know what the 3 gluon vertex looks like. It's a long expression. Only thing that matters in this limit is the 2I p mu, but there are some caveats. Okay, so and it conserves, and the spin here is the spin here. Somehow this gluon talks to all spin states in the same way, and it doesn't change the spin of this particle. There's a reason for this kind of the way you should think about this is that a gluon, so the coupling between gluons and matter is like this, or the coupling between gauge bosons and matter is like this. So there's a gauge field or vector index. It couples to some color current or some electric current if it's a photon. So the question in the gauge coupling, the gauge in interaction with gauge bosons is always, what is the current that you're coupling to? Now this current, if you have one single high energy particle, what is its current, right? Its current is a vector. It's a vector that has to depend on some other vectors. What are the vectors that you have available? There's the momentum of the particle, high energy particle, and the spin. The non-trivial statement here is that the spin doesn't matter, but that at high energy, the color current of a particle is always proportional to its momentum. And that's why the coupling of a high energy particle to a color field is particularly simple. It's always coupling the polarization index or the polarization vector of the gauge field to the momentum of the high energy particle. And that's it, because at high energy, it's only the the forward momentum vector matters. And that's the way gauge potentials couple to vectors. Now there's a caveat. Of course, you can work in different gauges, and this is not a gauge invariant. This is not a gauge invariant statement. In particular, what we will do in a couple of days is that we will choose a gauge where this polarization component does not exist, or somehow where the kind of the polarization of the gluon that would like to cut that this gluon the polarization of this gluon that most likes to couple to this particle is actually made 0 by a gauge choice, and then the diagrams that contribute look completely different, and then somehow physics looks different. So this is a slightly gauge dependent statement. The fact that it's this simple is a gauge dependent statement. Good, but I think this was everything for today. Apart from questions.
So I'm just checking. So these types of calculations doesn't only really work just based on the formulas that we're using. You can only do like a 1 to 2 step. And this device.
So I think that there's no limit to what you can do apart from your the amount of pencils and paper you have available. But I would take, let's say that the state of the art. The state of the art are calculations where you have a classical gauge field and is 1 to 2. The state of the art is something like 1 to 2 with one loop, or 1 to 3 at tree level, I think that's the state of the art that people are doing. But in principle, there's no limit. It's kind of how to treat the two. Yeah, in principle, there's no limit. Of course, in some sense, there are somehow 2 to 2 plus classical field calculations, but that's a little bit of a different way of doing the physics there. But in principle, there's no limit. Just that. But of course, one to when you say 1 to 2, it's 1 plus classical, 1 plus large classical field to 2 plus x. So in the because and so there's the 1 to 2, but 1 plus classical field, and the classical field, of course, is like a V1. In the classical field has a perturbability limit where it's just 1 V1.
You can also think about it as actually hitting, right, a pile of quantum fluctuations that together look like a classical field.
Yeah.
So counting, as mentioned, right, counting gluons in this situation is a little bit futile. Yeah,
you could think of it as 1 plus n, 2 plus.
It's only up to 1 group. Yes, there a technical reason why you want to go or just they just not so phenomenologically interesting?
Well, it's so this very specific in this specific it is it's technically more demanding. Kind of the fact that you want to keep the saturation aspect of unitarity means that you go back and forth between coordinate and momentum space. Whereas, I mean, if you do real loops and legs, people typically stay in momentum space, right? So there's additional Fourier transforms back and forth, which makes it more tedious. Somehow, you can, in some sense, you can try to formulate this in a more somehow more gauge covariant way. But then the calculators become even more complicated. So the simplest way to do these things is to work in light cone gauge for the projectile, but then light cone doing loops in axial type gauges is somehow typically not something that is done that much. It is done, but it's technically more complicated.
For a while, your line worked out.
there are,
yeah, that's one of the reasons why I would actually not do covariant theory in axial gauge. I do light cone perturbation theory in axial gauge. I think it's less ambiguities at the expense of potentially a little bit more work. Maybe. Yeah, well, it is a little bit more work because now every diagram for covariant theory becomes a couple of diagrams. Light cone perturbation theory is a little bit more work, but less ambiguous. But then it does get a little bit, I mean, it's not an order of magnitude more complicated, but it's and there has been so much interesting physics, interesting phenomenology already at tree level. And so that's why I think that's why it has also taken people a little bit time to before all the tree level, before somehow all that can be done at tree level is done. And only then you start thinking about loops. Maybe that's a big part of it too.
But at the same time, you need to go into one higher order from some sense of how certain your doable factors.
Yes. Yeah, so I think, but that's the during the last, let's say, 10 years, I think there are actually people out there systematically going to one order. Or then
and we're trying to understand how this relates to other observables where these high loop calculations have been done. That's things that we're looking at to see and compare. To understand whether we are actually doing this right or we are missing things. Go to next order. There's immediately a question of things that look subleading in terms of next to leading order corrections that are unfortunately not as small as you would like them to be. And then there's the question, how do you sum these extra corrections? So that partially also motivates us to compare to other calculations, right? In other, well, at first sight, unrelated fields where some of these things have actually been done. And then, right, that takes some time to actually take into account in the formless models.
Now I think we should go for a break.
We should go for a break. Well, let's actually make it half an hour break and then reconvene again if there are any questions. I do encourage you to ask questions. There should be a lot of stuff that could do with extra explanations what went into it or not. So don't just run away. I hope there is a little tea and coffee set up on the other side to let us relax here. Okay, let me stop recording here.
Yeah.